Welcome back, everybody. Today we are discussing the Boussinesq equation. This is basically the general groundwater flow equation. So last time we looked at an unconfined aquifer with recharge. So that was, the steady state equation, but with a source term. The Boussinesq equation basically is looking at what happens when things are not steady. So again, if we remember from before, what we've done is dq prime dx equals 0 for the unconfined and the confined case in the very first lecture. This last lecture with recharge, we had w. And now today, we're looking at the case where there is unsteady flow. So the water table might change in time. Okay, so again, for an unsteady state, what we're basically looking at here is going back to our mass balance lectures and figuring out, in minus out equals accumulation. So what is that accumulation term of that unsteady state? Where is the water going? And again, we have to take a little detour. We already talked about this before, lecture 2.7 here. But if there is an unsteady flow on the right-hand side, you can see that the problem with the groundwater, right, or the porous media, is that the water, the change in head or the change in water level, if you will, for an unconfined case, is not just the water level times the porosity, but really the storativity. So here we start with the mass balance, right? dq prime over dx equals dh dt, and now we have the storativity just to make the water quantity, the mass balance, right? Now we can replace q prime with the Darcy's law, right? And it's equivalent, so like we've done before, so we have this expression here. Now we're saying if k is constant, so that's been an assumption so far, but if k is constant, again, we can pop it out of the differential, right? So k is here now, and then of course we can change sides, and now k is at the bottom. So all of this is still equivalent as long as k is constant. Now finally, we arrive at that dilemma that we've had before for the unconfined case where, h is the variable, and that's a problem because we have to keep it in the math. Now, in this case, we're going to do a leap, and that's what the Boussinesq equation really is about, is we basically linearize this problem by saying, well, if h is deep enough, or if the aquifer is deep enough, then the change in h is very small compared to h, or h is very large compared to the change in h over x, right? So if you have a 1% slope, right, in an aquifer that is, tens of meters or hundreds of meters deep, then, this quantity is very small, or the depth is very large, so basically h is a constant, right? So if we assume that h is a constant, then we're going back to that confined case that's very simple, right, where we say, well, if h equals b here, right, basically we're back to that confined case, it's a constant, then same thing, we can say, well, we can just throw it on the other side and say, well, now the equation is d squared h over dh squared, and notice we don't have any square here because we just assumed it's a constant, so we don't need to carry it in the integral. So d squared h over dh squared, excuse me, this is not focusing, there you go, equals s over kb dh dt. Okay, so now we have a much simpler integral, and that's basically the Boussinesq equation, again, for a homogeneous, so for k constant, right, so for something that doesn't have changes in k, and also assuming that h is constant so that we can throw this on the other side. And this is the definition of transmissivity, right? So q prime equals q over w equals kh dh dx, again, kh dh dx. If we say kh equals kb is constant, that kb term is called the transmissivity of the aquifer. Now, this is really important because, so in the next course, there's the second course of that 3 1-credit sequence is on Wells hydraulics, right? So if you're interested in Wells hydraulics, when we do Wells tests, basically when we want to know the properties of an aquifer on a property, typically what we want to know is the transmissivity, because again, the transmissivity is basically the capacity of the aquifer to give water, right? So as far as the water resources go, this tells us, how much water we can get from that aquifer. So this is a really important parameter that typically that's what we want to calculate. Okay, so now finally we have this equation here, storativity over transmissivity on the right-hand side. Just a one last note. So this is again the basic Boussinesq equation without source terms and with a homogeneous hydraulic conductivity. So same hydraulic conductivity everywhere. Just a quick note here is that if you send the S over T on the other side, now we have an equation that reads dH dt equals some kind of a constant that's a property of the aquifer times the second derivative, spatial derivative, d squared AH dx squared. Now this is, if you've seen it before, right, this is basically the heat equation or the diffusion equation. And again, that is related to our third module here where we'll talk about contamination and transport a lot. So that diffusion equation is a classic equation, or heat equation is a classic equation. The reason I mention that is that there's a lot of solutions basically for problems with diffusion equation, even with source terms like the wet, the rain or the leakage that we'll see in that next lecture. So there's a lot of knowledge accumulated on these types of equation that we can solve for different situations, different boundaries, etc. So it's a very well-known equation, if you will, that we can deal with. Okay, so this is all for today. In the next lecture is a very short look at leaky confined aquifer. So confined aquifer that have an aquitard or something that leaks water on top of them, and we'll see how that affects flow. So again, it's a problem with source water basically on the top. Thank you.